particle in a box. So I'm on page 31 of my notes. I'd like you to follow along. I'm seriously just writing out everything that you're seeing, but there is a bunch of stuff I'm going to skip just to expedite the fact that I don't want you to have to sit in front of a very long video. Okay, so the particle in a box. Why do we care? A very simple model is something that's really important to start with. For ideal gas law, we always start with that when we're talking about any sort of thermodynamics, because when you have a couple of points, gas particles, you can really think about the different energies that they're going to contain. Same thing with the particle in a box. What we're aiming to get towards is where we have a proton with an electron bound to it. So what we call boundary conditions, or something that confines the electron to a specific type of space. Now, the Coulombic interaction between the nucleus, the proton, and the electron, that's going to add a potential. That's going to complicate things too much. So that's one of the reasons that we put our electron in a box. There's our electron. It's in a box. It's going from 0 to A is the length of the box. And I draw these little arrows up here, and I say that this is a function of the potential energy. And so the potential energy, which I'm going to represent as V, is equal to infinity outside the box. And inside, V equals 0. So you can think about this as a height potential. So basically you have an infinite wall, and the electron is confined to this region to where there is no potential. Cool? Which is very convenient for us, because when we use the always time independent for this class, Schrodinger equation, we're going to say, all right, h psi of x is equal to E psi of x. Now, like I told you before, the two questions that we want to ask is where's the electron and what is its energy? Well, in the box we can only find the probability of finding the electron, or we can find the expectation value, which would give us, after many measurements, where the electron would be within the boundaries of this box. Or we can get the energy based on the conditions associated with putting that particle in that box. So let's look at the Hamiltonian first. So we've got minus h bar squared over 2m, since we're just in one dimension, d squared dx squared, plus, there's my potential, which I sadly have written as v, but there we go. So the potential energy. And so because inside the box we've set that equal to 0, we're actually only looking at the kinetic energy. There is no potential energy associated with the box. Side note, when we get to adding on electrons to the hydrogen atom, there will be a potential energy here, and that's where the mathematics is going to get a little bit more complicated. So we're going to start with easy, and then we're going to move towards more complicated. Okay, Hamiltonian goes to 0. That's fantastic, because when it operates on psi of x, it's still going to give us E psi of x. Let's make this a little cleaner. So minus h bar squared over 2m d squared dx squared. Psi of x is equal to E psi of x. All right, I'm going to clean this up a bit more and move all of this junk to the left-hand side, or whatever side that is, now that we're going to flip it around. Psi of x is equal to minus 2me over h bar squared psi of x. Okay, so to make things convenient for us, I'm going to take, because I know where I'm going, but so do you, because you have the notes in front of you. I'm going to take all of this stuff, this coefficient of 2, the mass, the energy, divided by h bar squared, and I'm going to call this k squared for convenience. All right, so that equals 2me over h bar squared. All right, so now this is part of the course where I tell you that you learn to turn the handle in class with me. Once we get the result, then you go and take that result and you use it in your homeworks. I don't think I have you doing any of these, solving these differential equations by hand in the homeworks. If I do, it's good for you, so you should do it anyway. But this is the mechanism is how you would do that. And it all comes about by just trying general solutions. This is the ultimate in guess and check. We think we know what sort of wave function that this should be, so we're going to just try one and see if it works. So we're going to try the general solution of psi of x is equal to a sine of x plus b cosine of x. Now luckily we have somewhat of an educated guess on this because we know that this electron is going to move in wave-like motion. And so sine x plus cosine x is going to give us wave-like motion, and I should actually, sorry I didn't look at my notes, there's a k in there. So it should be sine kx plus b cosine of kx. I got excited, sorry. Equal to psi of x. Okay. So there's some conditions that I want to teach you about using the boundary conditions and the knowledge of the boundary conditions to tell us what's going to happen at these edges, and that's going to help us identify what these coefficients are and if this is actually a legitimate wave function that would satisfy our equation. Okay, so since the probability of finding the particle outside the walls is 0, we know psi of x must be continuous. And since we know that it must be continuous, if the probability of finding the particle outside the box is 0, that means that if the wave function is going to approach b0 here, then it also must be 0 at the boundary. And so that information helps us know that psi of 0 must be 0, which means a sine kx plus b cosine kx must also, oops, our x's are zeros. So now the question is, sine of 0 is equal to 0. Cosine of 0 is equal to 1. I don't even get to pause and have y'all answer the question. Yell out if you can. Hopefully you're sitting by yourself watching me go crazy with quantum. Okay, so psi of 0 gives us 0 plus b cosine of 0. This part is equal to 1, which means b has to be 0 because, again, this whole thing is 0. So that's convenient. So now that we've reduced, based off just the edge boundary condition, we've reduced our guessed wave function to be psi of x is equal to just a sine of kx. Sweet. All right. Now, what about the other side? At the other boundary of a, we have to have the same thing happen. So psi of a has to also equal 0, which means a sine k of a has to equal 0. And so the only time you can get sine equal to a 0, think about your whatever this is called, unit circle, or just a sine wave. So sine of x equals 0 at 0, pi, and 2 pi. And so this is a way to say that every time that this sine ka, so if ka equals n pi, so anytime it goes through any value of pi, then this whole thing is going to equal 0. So now we have a condition that says that ka is equal to n pi, which means k squared a squared is equal to n squared pi squared. But we know that k from over there, notice I had this k squared for convenience. So I'm just going to move over here. So we've got k squared is equal to n squared pi squared over a squared. And that whole thing, if you stick it into this equation, gives us our energy, which we know works because it's going to work with this wave function satisfying the Schrodinger equation, is equal to h bar squared n squared pi squared over 2ma squared. Okay, and so those are the energy states of the eigenvalue equation, and I'm out of time. Ta-da!